Yes. Hey, welcome back again. Yeah, I know. 2 videos a day. It's not impossible, but well, you can't stop me from uploading. Can you? Yeah. Today, now, let's go over the problem. Bipartite graph. So, in other words, you'll be given an adjacency matrix and you have to tell if the graph created from the adjacency matrix is actually a bipartite graph. And what does bipartite mean? It means that if you color one node with a single color, then the other nodes which are connected to it must be a different color. And we can use only two colors. That's what bipartite means. For example, you have two colors like they are used blue and green. And if one is colored as blue, then all its neighbors must be colored green, and all the neighbors of one should be colored blue. It goes on like that, and you just have to tell if the given graph can be the color like that. In other words, if the given graph is a bipartite graph, then you have to return true, or else you have to return false. Yeah, again, just read the problem statement properly. Uh, yeah, okay, yeah. Just read the problem statement properly. And yeah, the vertices start from 0 and go till n or v vertices will be given. So again, it should be pretty obvious that whenever you are given an adjacency matrix, the first thing you have to do is to build the graph. So let's do that in autopilot, and then we will talk about how to actually solve the problem. Yeah, again, to do a graph, you need to have a default dictionary. And so what you have to do for uh, the thing is again, let's look at the input, some input. Yeah, so it's given like that. So the edge, the incoming edge, the outgoing edge, the incoming edge, the outgoing edge. So it's given like that for E1 comma E2 in ADJ. Define the repository or graph. Yes. So graph at the position E1 dot append E2. Yeah. I think there's some issue with indentation. Yes. Now, yeah. Let's just return false and print the graph to check if you have done the mapping properly. Yeah, and don't forget to type the spelling of collection properly. I think I failed in fifth standard or something. So I okay. Why is it happening like that? For I in ADJ, I. Okay. Is it not given in form of two values? Yeah, it is. Okay. Okay. This is misleading again. So what they have done is for each index. So for zero index, it is mapped to 2, 3. For index one or the node one is mapped to one. It's given like that. So we can't do like this. So what you have to do for I range length of ADJ, for J in length of ADJ at the position I. What you have to do? You have to do the same thing, but you have to take J, and to that you have to append ADJ at the position I, at the position J. Yeah. Just run the code once and you check how the input is given and all. And yeah, now we have the actual mapping. So 0 is mapped to 2 and 3. I think this is the second question over here. 0 is mapped to 2 and 3. And 1 is mapped to 3. 2 is mapped to 0 and 3. 3 is mapped to 0, 1 and 2. Yeah, that is what we wanted to see. Now it's working. So now just think of what you have to do. So you have to color each node. So yeah, I think the best thing to do would be to take two sets. Let's call that. Yeah, let's take it the color which is given itself. Yeah, we'll have two sets called blue and green. So and what we will do? That there is one more thing over here. The thing is, I really got tripped up while doing that. And the thing is that it is not necessary that all the nodes will be connected. there might be two different graphs also. Like this, in the forest, there can be many trees. So in this forest, there can be many graphs also. They have not mentioned that specifically. So first time I was doing it, I got stuck up in that, and I was not understanding what was the mistake. So yeah, and since I know that, and since now you know that, it should be again easy to do. What we'll do is we'll have two sets called blue and green. Each holds the nodes, and then we will have a flag variable. And yeah, it does not matter what you set it to initially. And what we'll do is, as soon as we append one node to it, we'll change the value of flag and check if the nodes which you have put inside, like all the neighbors of the node which you are putting inside, if they are the same color, that means that the two nodes are of same color, and that should not happen. Like imagine you put two in the node, and then what you did, you are going to check if its neighbors are of color are present in blue set. Since you put two in blue set, if the neighbors of two are present in blue set, that means that you obviously could not. This is not a bipartite graph, so you return false. Or else what we'll do, we will take the neighbors and put it in green. So we'll just do that. We'll take a flag, and as soon as you put this in green, we will again flip the flag, and then put all its neighbors in blue. Yeah, we'll do like that. That's why I have taken a flag. So what we have to do for each node, for it's not node, yeah, it's node only in range V. This is because the nodes are given from 0 to B minus 1. So we will go from 0 to B minus 1 only. And what we'll do, if the node is actually present in green and blue, green or blue, that means that it has already been visited and colored, so we will not take it into consideration. So if the node actually exists in green or the node actually exists in blue, so what you have to do, you have to continue because that has already been checked. Or if what we'll do, uh, yeah. So what we'll do now, we will declare the two sets. Yeah, be careful of indentation. Yeah, now declare the two sets which you want to do, and then declare the flag. And yeah, again, I don't know why I'm doing this. This should actually be outside only because if the node is visited, then you have to add it outside. That you should not reset the visited set after each node iteration. Like after you finish iterating from a node, you should not reset it. So yeah, we'll have a flag is equal to true. And again, I'm doing BFS over here. So you can, I don't think you can do DFS also, but I prefer do BFS. So again, to the obvious, you have to import the DQ. The Q is DQ. It actually contains the current node which you're on. And while the queue exists, so what you have to do, go through all the go through the entire queue, and then pop out the node. Yeah, and you have the current node. So what we have to do, if the flag exists, then we put it in blue set, and then check if the neighbors of it exist in blue set. So if the flag exists, so what we have to do, if the node exists in green, that means what we'll do, yeah. Okay, if the flag exists, that means we'll put it in green, and then if the neighbors also exists in green, that means we obviously could not reach that node. So what we're doing, we are actually putting 0 in blue, and then we are telling check its neighbors, and then check if it is in green. So first, initially what we are doing is we are just directly checking if 0 is present in green. So if 0 is present in green, that means we'll directly return false. But initially the entire hash set is empty, not hash. Yeah, and the entire hash set is empty. So then we'll return false. Or what we'll do, if the node exists in blue, yeah, then because we were actually right. Or else what we'll do, to blue we will add the node. Else if the flag does not exist, so what we'll do, we'll do the same thing actually, but we'll actually do it on the opposite color. So if node exists in blue, then the return false. Or if node exists in green, continue. Or else to the green, you add the node. So after doing this part, what you have to do, you have to flip the flag. Like after adding all the nodes, you have to flip the flag. So yeah. Now we'll not directly jump to that. So now we will actually do the DFS part. So for neighbors, So what we'll do, and after doing everything, just flip the flag. And if the entire loop ran, like all the nodes visited, that means that the graph can actually partition as a bipartite graph. So we'll return true. Yeah, we'll just turn it once. We check if it works. And it's working. Let's just submit it. Yeah. Okay. Okay. And don't look at this sentence. That is, I got really tripped up mainly because they had not mentioned anywhere that the actual graph was could be disconnected. Now I'll just go through what is happening. So first, initially, what we're doing, we'll start from zero and we'll add zero to the queue and then pop out zero. And then you're checking if flag exists. The flag exists, then check if zero is actually present in green. And initially, zero, green and blue both are empty. So we'll just continue. So what you'll do, yeah. So initially, since flag is true and zero is not in green, so to and yeah. So in what we're doing is we are considering zero to be in blue state. So since flag exists, to blue we will add the node. But before adding the node, we'll check if the node is actually present in blue. That means that we have already added the node one. So we'll just continue. But if the current node actually exists in green, that means that this node was actually blue, but it had to be green. That means that this node was actually green, and that means that we obviously could not do anything. That means we have to return false. So we are returning false. Once we're adding it to blue, or else what we're doing, there is no flag. That means that the node had to be green. So if the node was actually blue, that means we're returning we are returning false. Or else we're adding it to the green, like we are adding it to green set. And yeah, I think it's better if I just uh, do it on some node which actually has a good input, like which is true. For that, again, I have to write a bipartite graph. Yeah, we'll not make it too complicated. We'll just do this. So there are three nodes with two edges, and it is the mapping is 0 to 1, 1 to 2. Yeah, let me just print the blue. Yeah, now check. So what is happening is 0 and 2 are actually present in blue. Over here the color is inverted, but that does not matter. So what we are doing, we are initially adding 0 to the blue queue, and then what we are doing, okay, now yeah, and then we popped out 0 from queue, and then if the flag actually exists, initially what we are telling is we are telling that flag, yeah, if you make it, then it will be added in reverse order. Yeah, for the sake of keeping up with the actual example, we will do it like this. Yeah, so as you see, 0 is present in green set. So what are you doing? Since flag is not there, and yeah, both the conditions will not evaluate because node is actually not present in blue. So this will not work, and node is actually not present in green also. So this also will not work. So green to green will add the node, and for all the neighbors of the current node, which is one, the current node which is 0, we will add it to the queue. So only one will be added to the queue. And again, for the node 1, what we'll do, we'll pop out the node. But now the flag is actually true because the flag has been flipped. So when then we'll check if one actually exists in green. That means that the neighbor of like its parent was actually blue. But the thing is, one actually does not exist in green. That means that this condition will not evaluate. And since node also does not exist in blue, this condition also will not evaluate. So to blue, we will add one, and then again we will go through all its neighbors, which is only two. So two will add to the queue, and flag has already been flipped again. And since flag is not true, we will again go to this condition. And two actually does not exist in blue, and the two does not exist in green also. That means that we will directly add green to our node. So and what will happen is that by this time all the nodes have been visited, and yeah, and as you see, they were actually properly partitioned into two subsets, like one which is of all of blue and one which is all of green, and that's how the algorithm works. I think there's one more way to do it also, like they use an array list to keep track of which nodes have been visited, and yeah, but this is also a good way to do. And if you want, you can just check out the array list part also because I did not do that. And yeah, that's all for it now. So after this video, if you know how to check if a given graph is bipartite. Yeah, that's all for it. Again, I'll tell. Yeah, you will fail a lot of times, and yeah, you will fail a lot of times, and it will happen. And don't get disheartened, because if I gave up after I reached over here, then like it's pretty obvious that I would never reach the correct solution. So always just keep on trying, and at one point of the or the other, your hard work will definitely pay off. Again, see, so many submissions are there. And yeah, that's all for it. Keep on grinding more DSA. I know you can do it. Yeah, thank you for watching. See you next time. Bye.